think we are live. Just give it a second. Pop out the chat. See how everyone is doing. Guys, let me know how you're feeling about A-level chemistry paper 2. Organic, we know is a memory game. We're going to be doing a bit of NMR and a bit of unseen mechanisms. So I've got 5 NMR questions if everyone is happy with that. Just going to get my TikTok live going. We're going to start with the 24 NMR question first. You guys are not finished. You're not finished. Trust me, you're not finished. Here's your first NMR question, guys. You feel free to have a go. It's 2024. I don't know if you guys have seen it before, but feel free to have a go while I just get this TikTok up. You guys trust me. You will be, or you're more prepared than you think you are. So that's something. You guys will be fine. Let me know how you guys are feeling, bro. I'm finished. Very sad. Yeah, you guys will definitely do better than you think you will. I'll tell you that for free. Everyone always thinks they're gonna do bad going in. You come out, you get 95. So I wouldn't stress too much. Would not stress too much. It's just getting my TikTok live up. Feel free to have a go. Any of these questions, oh, sorry, add the NMR question on there. Just gonna wait for a few people to join as well before we start getting into the question, making sure the stream is in excellent condition. Oh, it's lagging for me. Give me a second, guys. Okay, it should be fine. All right, there we go. All right. TikTok live is up. What did I get my A-level chem? I got an A star. I did get an A star. Organic was by far the best for me. I did, and still do quite enjoy. You guys can all get A stars. You can all get A stars. I'm just gonna give it a couple minutes, maybe 1 or 2 minutes before we get into this question. Guys, I'm gonna have to do it on OneNote with my mouse. I apologize in advance, but not really much else I can do at this point. We're live on YouTube. If anyone's on TikTok, live on YouTube. We're gonna go through 5 NMR questions. All proton, obviously. We're not here for carbon. I got 3 A stars, so I think I can help as much. I would try help as much as possible. I did get 3 A stars, so I'm not making stuff up here. I'll try not to at least. How many marks for an A in OCR? It was high last year for organic. I don't know about the whole thing. 243. All right, guys, give me a thumbs up if you want me just to get going. Give me a thumbs up. Give me a thumbs up. It's already 8:05, so I will be getting going maybe in just a minute. When I see thumbs up, I'm gonna start going through this question. Wait, would this question also appear in AQA? I would assume so. I would assume so. I would hope. Yeah, I hope I can help, guys. I hope I can help. But worst case scenario, I have some notes. I have some questions. If I'm waffling, you can still use the content I put on the screen. Still going to be helpful. 78, 79. Was that? Oh, for an A, for an A. I was going to say for an A star, it was high. It was like what, 80 something percent? Alright, I'm seeing some thumbs up. Gonna wait for a couple more, and then we're gonna get going. Once again, guys, I'm going to have to do it on OneNote like this. I apologize in advance. Can I go through the mechanism? All the mechanisms? Oof. Maybe. Maybe. How do you think I should spend my extra time as I end up finishing at the same time as everyone? Wait, how do you think I should? If you have additional time, then just keep looking over questions. I mean, that's what you can do, right? You're not in that exam for too long. It could dictate your whole life, guys. Not your whole life, but if you want to go to a certain university and you're on the edge of the grade, use the extra time just to check. That's what it is. Mainly doing maths. This year was mainly maths at university for me. I'm doing a joint honours, but it was basically maths this year. When am I going live? Until we're done. Until we're done. We'll see. We'll see how long it takes. 5 NMR. Um, 5 NMR. 4 unseen mechanisms. 806, guys. Let's get going. Let's get going. Right, 2024 question. We're gonna have to take it step by step because I can't get the whole thing on my screen at once. All right. Let me get that pen up. And let's get going. All right. So we're given the elemental analysis by mass of compound J. So we're told we have our carbon, we have our hydrogen, and we have our oxygen. For carbon, We have 80.6. Remember, we can take 80.6. We can take this as the mass, guys, remember? And we're going to divide it by the MR. And then 11.94. We like each of these. So we're going to do 80.6 divided by 12. This is to get the empirical formula. 7.46 divided by 1. 11.94 divided by 16. I apologize for the handwriting, guys, but it will be clearer for the spectroscopy. All right. So put this in your calculator, guys. 80.6. I'm going to write out every decimal place, but here we go. 80.6 divided by 12, we get 6.717, more or less. 6.717. 7.46 stays the same because we're dividing by 1. And then doing that, 11.94. That says 11.94, guys. Look at the right hand side. 11.94 divided by 16. We get 0.74625. 0.74625. Okay, it's not neat, guys, but you can see the numbers here. This is just for the empirical. And then we divide by the smallest one, so we're going to divide it by all of this 0.74625. Let's call it A, because I'm not going to write out the whole thing every time. So we divide by A, then we divide by A, and this is obviously going to be A divided by A, so that's just going to be 1. We have 1 here, I'm doing 7.46. 7.46 divided by 0.74625 gets us around 10, and then doing it for carbon will get us around 9. So we have 9, 10. So we have our empirical formula to be C9, H10, and then a single O. Now we're going to compare it to the mass spectrum, guys. Look at that largest peak. That's what we really care about in this case, to find the total MR of an organic molecule. That says around, if I look closely, 134. Let's compare that to our C9H. Let me draw that 10 a little bit nicer. That's C9H10O. So we have C9H10O from here. So we do 9 times 12. Answer plus 10. Answer plus 16. Gets us 134 in the calculator. So this empirical formula is actually our molecular formula. So we already have the molecular formula of C9H10O. This is very useful. We know there's already one oxygen. That's a horrendous oxygen. So from here, we look at the IR spectrum. Let's look at the peaks, guys. Let's look at the peaks. So we have this smaller peak at around 3,000. It's a bit messy, guys. Oh, Jesus Christ. It's a bit messy. When we see these messy peaks, we start thinking of benzene normally, but let's just take a second. So we're going to ignore this peak for now. Or we can, you know what, let's look at it, guys. So we're seeing that peak at around 3,000. Look at around 3,000. It can either be an alkyl group, alkenes, or arenes. So we're going to keep that in mind. So we have that peak at 3,000 will either be, I'm not going to write each thing out, I'm just going to write either the alkyl group, keep it in mind, we'll see what the proton NMR tells us, but we're going to carry on from here. Or we could have an arene, so an aromatic benzene ring. So that's what we know so far. Looking at any other peaks, what are the peaks we have? We have that fat peak at 1,000, just beneath 1,700, I'd say around 1,700. So it looks slightly above the alkene. It's going to be that C double bonded to an oxygen. So we know that oxygen is going to be a part of that C double bonded to an oxygen. We don't know the functional group just yet, but we know this is going to be the case. Okay? So we have peak at, what was it, around 1,700. Just keep it. That carbon double bonded to an oxygen. Okay, this is good. What's an arene again? Benzene. For mass spectrum, do you just take the peak with the highest number as the MR? Yes, you do. Sometimes there may be an isotope, but if you can kind of see, like, if your empirical is very, very close to if you're one off, especially to your mass spectrum, then you know it's going to be you know that's going to be the MR. The key thing is to see if we have to multiply our empirical formula to see. That's the key thing. See if we have to multiply by 2, 3, whatever. Earlier today we saw we had to multiply by 3 because the MR was 3 times as much as our empirical formula MR. So we have C9H10O. We've identified these two peaks. We're not 100% sure what the one at 3,000 will be. We see the 1630 to 1820 carbon double bonded to an oxygen peak. Then we have this fingerprint mess. Let's not focus too much on that. It's a bit of a mess now. Let's look at the proton NMR. We might have to go back to this, but let's just leave it there for now. So looking at that proton NMR, we're going to fill out our table, guys. So let's go from right to left. You can do it either way. Always be conscious about the other peaks, because sometimes you might think there's a certain bond in an earlier peak, but because, for example, here we only have one oxygen, so we know if there's an oxygen bond at a later peak, we can't consider the one at the earlier peak. That's just a key little thing to try and think about. But let's go. So 3 hydrogens, doublet. Start filling the table out, guys. Start filling the table out. 3 hydrogens, and then we have a doublet. N+1 rule, guys. That means we're going to have one adjacent hydrogen. Chemical shift, let's go back and see. I believe this was the first one. So this is just a 1 point, doesn't matter really, 1.5. It's just going to be that alkyl group. So what are we thinking, guys? What are we thinking? Well, we're going to have a carbon. We're thinking there's going to be three hydrogens attached to it. And also, when we have CH3, we know this is going to be an end of the molecule, right? It has to be the end of a molecule when we see CH3. So when we're piecing this together, this will help us just to go through it. And then I'm going to draw it in red, guys. We know in the adjacent carbon, there'll only be one hydrogen, and I'm going to have two bonds going to other things. Because the N+1 rule, we have the doublet, only be one hydrogen. Tell me if I'm going too slowly, guys. Tell me if I'm going too slowly. Then we have one hydrogen, and that is a 1, 2, 3, 4, 5. That is a quintet. So we have one hydrogen. We have a quintet. So what does that mean? N+1 rule, four hydrogens on the adjacent carbons. Chemical shift, let's check again. Let me know if I'm going too slow. Let me know if I'm going too slow. This will be at 3.8 approximately, I'd say. Maybe 3.7. Up to you guys. Let's say 3.8. So looking down at 3.8. Looking down at 3.8, we can see, well, we can't have a chlorine, we can't have a bromine, because they're not in our molecular or empirical. So there's going to have to be the hydrogen bonded to a carbon, which is then bonded to an oxygen. We only have one, so we're going to have a hydrogen to the carbon, and then we're going to have an oxygen. Oh, sorry, wait. Hydrogen on the carbon, yeah, and then to the oxygen. However, we do know that this will have four hydrogens on adjacent carbon atoms. So we know that it's going to be some kind of, most likely because it's going to be four, we know it can't all be on one carbon. So we're going to have at least have two carbons bonded to this carbon in order to have those four hydrogens. Just a good thing to think about as we go. This is a quintet. I think I saw five there. Quintet. 1, 2, 3, 4, 5. Yeah, five quintet. So it's going to be four adjacent, or four hydrogens on adjacent carbon atoms. Continuing on. Okay, we have five hydrogens with this massive singlet peak. We know when we see singlets or like really messy peaks, we're already thinking benzene. We're already thinking that. And five hydrogens, we're going to have five hydrogens in this environment. Okay, cool. So we have five. We see this singlet. But keep in mind with this benzene and these weird peaks, you have to kind of not take this too seriously. And then what was the shift? About 7.2. This should confirm that we're going to have that benzene ring. But let's check. 7.2, exactly that. So we have five hydrogens attached to a benzene, because there's five in that environment. This is really good. So we know we can draw out our benzene ring. I've been criticized a lot for my benzene rings recently. I apologize. So we know five of these will be not bonded to anything. We're going to have five, because this is C6, we have five environments, so we're going to have five. Well, I'm lagging, guys. Let me know if it's really bad. We're getting hot? Not hot yet. Okay, and then around what? 8.99, we have a doublet and with one hydrogen. Okay. So one hydrogen, we have a doublet. Therefore, we're going to have one hydrogen on an adjacent carbon atom. And then quickly seeing where were we again? We were at 8.9, 8.9. Well, it have to be 9 here. Okay, cool. So we know we're going to have an aldehyde. We know we're going to have an aldehyde. This is good information. It's great they're telling us this. So we have that carbon double bonded to an oxygen. And then here is our one hydrogen. And we're told that there's one hydrogen on the adjacent carbon atom. So if we draw out that adjacent carbon atom, we know there's only going to be one attached to it. And then we're going to be going off in two different directions. Okay? So we can just call that shift 9. I believe it was 9. Yeah. So this is good. Let's start piecing things together. Let's start piecing it. Why it's 5 for benzene? Because we have 5 hydrogens in this environment. We have that chemical shift where we would have that benzene ring. Going back, where we would have that benzene ring. And there's 5 in that environment. Okay? So let's just piece it together, guys. Let's kind of see what we know and see what we can take off. So we know we have the benzene ring. We can immediately draw that on. Okay? So we know we have that benzene ring. Bing, bong, bing. Confirmed in two places. Confirmed in both the proton NMR and that potential peak that we considered could be the benzene ring on our IR spec. So 5 of these will be not bonded to anything. Then from here, we can kind of work through. So we see. So guys, remember we are going to have to experiment a little bit as we go. We know this is going to be directly bonded to a carbon because as we saw, I believe. This is the key bit of information, guys. Because we have this oxygen down here, and we know there's only one oxygen, so you always have to be looking through this, guys. I'm kind of going along with you, thinking about the process, trying to use the information that we have. So because we have this oxygen down here, one single oxygen, but we know it's going to be used in our aldehyde, we cannot have all this here. We cannot have this hydrogen bonded to a carbon, which is then single bonded to an oxygen. We know we can't have that. So we can immediately get rid of that. Now let's think about it, guys. Okay, so that can't be the case. And we know that shifts are variable. If you're close to other electronegative things, this can cause you to shift a little bit further. So what could we have? We could have, and this will make sense, a hydrogen bonded to a carbon attached to a benzene. Because now we established we can't have this carbon single bonded to an O, can't have the Cl, can't have the Br. We also know it could be this indeed. It could be this is another thing we have to think about. But either way, it does feel like we're gonna have that carbon attached to the benzene. But now that I think about it, guys, because we're in a higher shift, it would make sense that if this hydrogen bonded to the carbon would be kind of essentially part of both of these. A hydrogen attached to a carbon, then bonded to a carbon, double bonded to an oxygen, because that would satisfy what we found earlier. And then also adjacent to that benzene ring. So let's kind of draw it out and just see what happens. And we kind of tick things off as we go. I would recommend in the exam just experimenting. I'm just trying to do it very methodically here. So let's see. In the exam, definitely just experiment and see if certain things work. Does it really matter if they'd allow a good ring yet? Because it's 6 hydrogens. Why do you take the aldehyde with the oxygen so the other one with the oxygen? Because this one can only be explained by this. Because we have that great shift of that hydrogen to the aldehyde, it can only be explained by this. However, this hydrogen with the carbon bonded to the oxygen could be explained by some other things, shifting it further to the left. So let's just kind of go from here. So let's just set it out, guys, and let's see what works. Once again, I have seen these before, so it may seem I do things quickly, but just kind of think carefully as you go through. No, you need to know more than what's on my notes. You need to know more than what's on my notes. My notes are just kind of like a brief summary. So we're thinking over here, guys. So we have this hydrogen bonded to a carbon. We also know, because it's shifted, it's very likely that will be attached to this aldehyde. So this is good. We already have the end of a molecule. Now let's just count how many carbons we have just from here and see if we can continue like this, because we may not be able to continue and we'll have to think about it again. So we have 6 in our benzene, 7, 8. We only need one more carbon. Only need one more carbon, guys. In terms of hydrogens, we have 1, 2, 3, 4, 5, 6, 7. Okay. Wait, sorry. 1, 2, 3, 4, 5, 6, 7. And we need 3 more. So what have we ticked off so far? We've satisfied this, because we have our aldehyde. We've satisfied this. And what else have we satisfied? We've satisfied the single hydrogen, which has that weird shift, more shifted to the left because it's next to that benzene and next to that aldehyde. So all we have to do is we have 3 hydrogens in a certain environment with 1 adjacent hydrogen. This is perfect. We have that 1 adjacent hydrogen here. End with the molecule because we have no more carbon atoms to use. So we can have a CH3, which works perfectly as we established back here, because it's bonded to a carbon, which only has 1 hydrogen on it. And this weird shift here, he says, this weird shift here that's slightly a little bit too far to the left for our liking. Because that current shift we just start assuming is a carbon single bonded to an oxygen, but this can't be the case because we've already used the oxygen on the aldehyde over here. Because this one, there's no denying. There is no way this will shift this far left without it being involved in the aldehyde. Whereas these ones, you can see some variable shifts. Can I post a link for a question? I can't right now. My computer will probably crash if I try to do it. Sorry. I'll leave the question. The other questions are smaller though, so I'll leave them up for longer. Guys, does that make sense? Do we have any questions? Because we also have those 3 hydrogens, and we satisfy that doublet. We satisfy that carbon double bonded to an oxygen. We satisfied that benzene ring, and we satisfied the C9, H10, and a single oxygen. Are we happy, guys? Thumbs up, or let me know if you have any questions. Why do I take it? Yeah, okay, it was because it was further to the left. So how do we know if it shifts? Why am I getting Borderlands 3? Okay. How do we know how do we know it shifts? Well, it's one of those tricky things. The kind of thing is we know there are variable shifts. If you're next to multiple groups, so for example, this hydrogen was bonded to a carbon directly bonded to a benzene, but also that carbon was bonded then to the aldehyde, we when you see this, it shift a bit. The shifts can be variable, sorry, and go more to the left. So it's the kind of thing that you want to leave to the end of the question. So in my notes, guys, if I actually go to my notes of this question, or let me go quickly go back up. So my notes of this question, let me zoom in. In my table, I actually wrote not yet, not sure yet. Let's see what's viable, non-viable. Yeah. Is it better to do this NMR question first or do it last? Do it last. You don't want to waste more time focusing on NMR. You want to be doing the questions which you can get marks on, guaranteed marks. And how would we say that in our working? Do we just say it shifts? I mean, if you get the correct answer, do you guys want me to show the mark scheme? Yes or no? I can't lie. If you do all the working of shifts on that table, exactly, that is true. If you show your table, you show your working, and then you just get one thing wrong at the end, or you feel like you can start justifying everything, you will get a lot of marks. So even though the original H carbon to the oxygen is not there anymore, do we disregard the four adjacent from the quintet? No, because we actually. Oh, sorry, not four. Oh wait, four. Yeah, four. No, we don't disregard it because how many hydrogens do we have? Sorry, I should have addressed that as well. Quintet, four adjacents. This hydrogen, one, two, three, four. It does have four hydrogens on adjacent carbon atoms. We've satisfied everything. Looking at each one, we have the hydrogen bonded to the carbon. Only have one hydrogen on an adjacent carbon atom. Then looking here, we have the three hydrogens, which we know with the doublet. So only have one on the adjacent carbon atom. And then with that one hydrogen, we have the quintet, four on the adjacent. So this is this hydrogen here. And then we have one, two, three, and then one here. So it would be four. Mark scheme, guys. Yeah, oh yeah, I'll put the mark scheme up. I'll put the mark scheme up. Oh, this might. Oh, sorry. I don't actually have. Oh, sorry, guys. I don't actually have the mark scheme for this question. Wait, one, two, three, four, five. Wait, is this the right mark scheme? No, this is not the right mark scheme. This is not the right mark scheme. This might have been for the question we had earlier. That's not the right mark scheme. Sorry, guys. I apologize. Do apologize. Are we happy to go to the next question? Thumbs up if we want to go to the next question. I'm going to delete all this now. So I hope that was okay, guys. Let me know if you have any requests for how we go through the questions. If you want it faster, slower, anything like that, let me know. Okay. So moving on, guys, I'm just going to quickly move off all of these NMR, all these questions, sorry. So I'm just going to delete them. I do have them on the other document anyway. I'm going to go to the next question. So I believe this might be a past paper question. I have a maybe not, maybe not, maybe not. I'm not sure. So guys, this is the next question. If you want to have a go, I'll leave it up for just a second. Good pace? Okay, good pace. Okay, that's what I want to hear. So guys, here's the question. I'm gonna leave it on for just a minute so you guys get a chance. I think we see NMR every single year, right? I can't recall a past paper where there was none. If you can fill out that table and potentially make a molecule which fills out some of the criteria, they're definitely going to give you some marks. They definitely will give you some marks. Just gonna leave the question up. Is it worth drawing the table? Yeah, always draw the table. Always draw the table, guys. Always draw the table. Unless it's a really easy question and you just see the answer. Like sometimes they put it in the middle of the paper and it'll be like worth 2 or 3 marks. It won't be the full structure. Then proton is more common. Yes, we will see proton NMR. It's definitely more common. Definitely, definitely. I keep getting confused on how to piece it structure together. Just trial and error, but always look at like what you know. If you have certain ends of the molecule, like aldehydes and CH3s, those are going to have to be at ends of the molecules. So it's kind of good to, or the benzene in that case, we knew that had to be one end of the molecule because it was then attached to one thing. So kind of think about what you have in the ends and put the pieces together. And obviously, like, just sketch things out. Like, just try certain things. If I don't get the final formula, but all the other information, how many marks do you lose? That's a good question. I mean, I guess it depends. If you get, I feel like if you get everything else, then you will get the very final formula, no? Feels like it. Could be wrong though. Could be wrong. I believe this was a past paper question. I believe this was a past paper question. And the ones after will not be past paper. Alright, I'm gonna start going through this elemental analysis by maths, guys. Give me a thumbs up if you're happy for me to start going through it. Actually, I need to start going through it. We have too many questions to get through. So going over the mass, we have 56. So let's draw out. We have a carbon, a hydrogen, a nitrogen this time, and an oxygen. Oh, that's too close together. Okay. So this is gonna be rough, guys, because it's just quick working. 56.69. Hydrogen was 7.09. I mean, this is way too close together. Nitrogen is 11.02, and then oxygen is 25.2. This is just so beautiful, isn't it? So carbon divided by 12, hydrogen divided by 1, nitrogen divided by 14. Oh my god. And the oxygen, we're just going to leave that there. Oxygen divided by 16. So this is very rough, guys, of course. So let's go through it. 56.69 divided by 12. I guess it's 4.724. I'll be a bit neater here. 4.724. Doing 7.09 divided by 1 is just 7.09. Then doing 11.02 divided by 14. That will give us 0.787. I'd recommend to write out more decimal places in your exam or just store them in your calculator. And then 25.2 divided by 16. What do we get? We get 1.575. Then we have to divide them all for the empirical formula by the smallest number. Smallest number is 0.787. We're going to call it A. We're going to divide everything through by A. Every single thing by A. My mouse isn't feeling very smooth today, guys. I apologize. C6H9NO2. Let's see if I think you are right. You are indeed correct. So if we have that 0.787, store it as A, alpha A. Okay. So when each one through, guys, we would get 6, 9, 1, and 2. Yeah, exactly. So we would have currently C6, H9, NO2, as someone already wrote in the chat very, very nicely. Quickly see if that adds up to our 127 peak, that largest peak. So we have 12 times 6, answer plus 9, answer plus 14, answer plus 32 is exactly 127. So we have our molecular formula. Awesome. Let's look at our IR spectrum. We've got a bunch of peaks here, quite a few peaks. Now this large peak here, the one around 3000, we know it tends to be that alkyl group. So let's ignore it for now. It could be an alkene or an arene as well, but let's kind of move on to the other peaks first, and it might help us from there. Because the other peaks could answer our questions just because we already know the molecular formula. So then we have a peak at around, what's that, 2200? So looking over, peak at 2200. Okay, we have a nitrile. So that's where our N is going to go to. So we have that one single N, so we do have a nitrile. So how am I going to draw this out? Let's just do that. We have the nitrile because we have the peak at let's just say 2220, sure. You could write down the range, guys. You know what, let's write down the range. But yeah. Then looking at other peak, this other peak here is about 1750, it appears. So that is going to be, we want to see some oxygens, exactly that. We have a carbon double bonded to an oxygen, 1630 to 1820. So 1630. Let me get my mouse a bit untangled, try to write a bit nicer. 1630 to 1820 is going to be that carbon double bonded, double bonded to the oxygen. Okay, so we have our infrared, we have our IR. So from here, guys, any more peaks that we think we can analyze? Everything below here tends to be fingerprints, so it tends to be a bit of a mess. Let's kind of move on from there and look at the proton NMR. So looking at the proton NMR, guys, move this paper out of the way. Proton NMR. So here's what we have. 3, 3. I'm seeing a triplet and a doublet. Let's put those in very quickly. 3, 3, triplet and doublet. 3, 3. Let me make sure I had all the correct triplet and doublet. So I'm not going to write the full thing out, I'm just going to write trip. Doublet, I think I will, just to not confuse anyone. Doublet, so the number of adjacent hydrogens, n plus 1 rule, that's going to be 1, that's going to be 2. Looking at the chemical shift, they're both going to be alkyl. We have one at 1.4 and the other one at 1.6-ish. Doesn't particularly matter where you say it because we know they're both going to be. So we have 3 hydrogens. Okay, this is good, guys. We have 2 times, we have these 3 hydrogens. So we're going to have a carbon. Same environment. Remember, they could be split up. You could have 2 carbons, maybe symmetrical somehow, so they'll all be in the same environment. But normally when we have this CH3, then we have 2 on the adjacent, this will be the end of the molecule. And then this one will continue to go. Then looking at 3 hydrogens with a doublet, similar idea. We're going to have that carbon bonded to 3 hydrogens. So this is good. We have another end of the molecule. Very useful information. And then we're going to be bonded to a carbon. Then we know this carbon will only have 1 hydrogen onto it and must be bonded to 2 other things. It's quite useful information. I'm happy they told us that. Then we have, at just under 3, maybe 2.9, we have a quartet. So it's going to be 3. How many was that, sorry? We had 1 hydrogen quartet. 1 hydrogen quartet. N plus 1 rule, so we're going to have 3 hydrogens on adjacent carbon atoms. Then what else do we know? What is the shift? The shift was 2.9. So 2.9, let's quickly check our table. Remember, guys, we have currently sorted out nothing. We've sorted out absolutely nothing yet. So 2.9. Okay, here we have a hydrogen bonded to a carbon, then bonded to an N. But it could also be this one bonded to a carbon, then double bonded to an oxygen. So we have 2 potential things that it could be here. So what I would do in this case, guys, is I would see further down the molecule if any of our oxygens are involved. I would recommend to do that just in general, because it tends to be pretty tricky, but let's check it out. So let's go on to those larger shifts first, just to ensure if we have bonds to oxygens, okay? Because we don't want to make any assumptions yet. So here we have 2, we have a 1, 2, 3, 4. That would also be a quartet. So we have 2, we have a quartet. And then we see, actually, guys, now that I think about it, this is the kind of things you can do as you're going. Now that I think about it, because the chemical shift is 2.9, and we know there's an N involved, there is nowhere else where we can have a nitrogen. So this has to be the hydrogen bonded to a carbon, bonded to a nitrogen. So we're going to have a hydrogen bonded to a carbon, and then bonded to a nitrogen. And it's only going to be 1. So this is going to have to carry on both ways. Let me know if that makes sense. Let me know if I'm going too slowly. So carrying on, chemical shift, we have that 2, that's about 4.3, let's call it 4.3. Quartet, so we had that 3 hydrogens on adjacent carbon atoms, 4.3. Let's look at that. It's not going to be an alkene, we know that, so it's going to be that hydrogen bonded to a carbon, bonded to a oxygen. And there will be 2 of those. So we're going to have 2 hydrogens bonded to a carbon, which then bonded to an oxygen, and we're going to have something else coming off this carbon. So let's start filling it in, guys. Let's start filling it in. So let's start with the end of the molecule here. Oh, this actually looks like we can pair up 2 things here, guys. Because we know this carbon will have 2 hydrogens attached onto it. We can also see the bottom, we're going to have something with 2 hydrogens attached onto it. So let's pair these up, because there's nowhere else which has 2 hydrogens, so we can immediately pair these up. So tick and tick. Let's draw it out. So sometimes when you see these things, guys, you think to yourself, okay, these have to match up because there's no other thing. That proton environment has to go with that proton environment because there's nothing else we can do. This is actually quite nice, because from here we know that these 2 hydrogens, they have, okay, 3 3 hydrogens on the adjacent carbon atom. So this is already sorted. That's perfect. And this one, the 3, only has 2. So these 2 both kind of satisfy each other. We satisfy this, we satisfy this, we satisfy this, and of course we satisfy this. And then looking down, 2 hydrogens, 3 on the adjacent. Shift 4.3, so now this has to be bonded to an oxygen, which makes sense, because we know that these 3 hydrogens here would be bonded to only 2 hydrogens on the adjacent carbon atom. So this is making sense so far. So of course, this oxygen is going to have to be bonded to something. So let's continue on. So what have we satisfied? We currently have, let's write it out back down here, guys. We have that C6H9 NO2. No, you don't need to, no, a lot of the stuff I'm writing, you don't need to write out. You do not need to write out. you need to write out your peaks. I'll go. I think that I do have the mark scheme for this one, so I can maybe I hope I do. I should. Anyway, from here, guys, what we thinking? What we thinking? What are we thinking? So we still need to sort out that N, and we need to sort out that extra oxygen. Looking back at the shifts, let's check out here. So we have this quartet, but we can also know that we're going to have that second oxygen, guys. We need that second oxygen. So because we have a second oxygen, but we don't specifically have any other area where we're going to be involving oxygens, this makes you think what kind of organic molecule, sorry, functional group are we thinking of seeing here? What are we thinking? What are we thinking? I'm gonna tell you guys, we need a second oxygen. But what I would recommend, you know what, guys, you can do this in different ways. I would just recommend experimenting, of course, but because we know this hydrogen will have a certain shift, we know these three hydrogens will not have any shift. So we currently have one, two, three, four, five. We need nine. So there's four more hydrogens that we have to address. But we also know only one of these hydrogens have a shift. The other one must have no shift. So one hydrogen will have a shift. So this carbon, thinking about it, guys, let's go back. We currently had that shift at 2.9, but we know where our other three hydrogens are. Ester, ester, perfect, guys. It's going to be an ester, but why? Because we know these three hydrogens are alkyl groups, they can't be involved in any of these ester bonds with a second oxygen or with a nitrogen. It can't be involved in that. So those other three must be part of the alkyl group at the end of our molecule, because we know it's CH3 as well, I believe. Let's just check that. Once again, exactly, we have three and a doublet. So now this is starting to come into place. We know we still need that nitrile group, and we know we have one hydrogen on this carbon which is shifted further to the left. So this will most likely involve both of this hydrogen carbon carbon double bond oxygen and hydrogen carbon bonded to a nitrogen. So exactly that. We have this hydrogen, one hydrogen here. We know it's going to experience a shift. So it would make sense to then have this nitrogen here, single bond to the nitrogen, sorry. Oh wait, sorry, I apologize. Because we know it's going to be a nitrile. Checking on. It's going to be to that carbon, and we form that nitrile. So I apologize, guys. I apologize. This hydrogen is only to the carbon double bond to the oxygen. So it's fine to make mistakes, guys. It's fine to go slowly and start thinking. As I'm doing now, I realize, okay, this doesn't work. However, because we have no hydrogens attached to this carbon, we don't have to worry. Exactly, exactly. Because this is nitrile, sometimes it just takes time to think about it. Because we look back at that infrared, we then see the nitrile. It's good to think back, go slowly, and then realize, okay, this doesn't work. Sometimes it's good just to quickly sketch. So this works because there's no hydrogens bonded to this carbon. We do have this hydrogen which has that carbon bond to the double bond oxygen. What do we have left? We indeed do have that CH3. That's all we have left with those hydrogens. Because also we could have counted, guys, counted our carbons. 1, 2, 3, 4, 5, 6. We have the C6. We have that 1, 2, 3, 4. 1, 2, 3, 4, 5. The H9. We have the nitrogen in the nitrile group. And we have those two oxygens and those ester bond. We have this oxygen because we knew we needed it. We have these two hydrogens with 3 on the adjacent. Shift 4.3 because we have a single bond to the oxygen. Then here, once again, we knew we had the nitrile group, so this couldn't have been the N. This had to be bonded to a carbon, which was then double bonded to an oxygen. So we now know that now. We went back to it and we can go over that. So exactly that. We had that carbon double bonded to the oxygen, and from there we continued on with that C to the hydrogen, because what did we know? We had that one single hydrogen, 3 on the adjacent, which made sense, and on the 3 on the end, sorry, we also had the doublet. So these kind of match up perfectly. We have that nitrile, just to fulfill our molecular formula and our infrared spectrum. And then this hydrogen has the shift on the carbon double bond to the oxygen. Does that make sense, guys? Thumbs up if you want the next question. Thumbs up if you want the next question. I'm going to quickly check the mark schemes, guys, just because I'm unsure of which mark schemes I have up. Well, I'm not trying to show all the answers here, but it looks like I might have to. 4, 5. I have 5 here. Hmm. This is the one we did earlier? I'm going to quickly check if this is the one we did earlier, guys, until I see those thumbs up for the next question. Okay, yeah, this was the one we did earlier. Okay, I can delete this one. Oh wait, I'm not on selected. Is everyone happy there, guys? Everyone happy? It's really delayed for me. Really, really delayed for me. I believe this is the nitro. Okay, here's the nitro, guys. So we have all these different options. The one that we put is somewhere on here. Here's ours, I believe. No, we need the ester bond. No, here's ours. So there's the mark scheme, guys. There's a mark scheme. Let me know if that makes sense. Give me a thumbs up or a thumbs down if that doesn't make sense. Thumbs up if you want me to carry on. Thumbs down if you don't want me to carry on. I'm gonna quickly check that the stream is all good. Looks like we're all good. Okay. You want me to explain the whole thing again? Okay. Okay, so what did we know? We know we had the peak with the nitro group. We know we had that carbon double bonded to an oxygen, and we know it had to be. So okay, we knew these two things, sorry. We had the molecular formula to be C6H9NO2. From here, we plotted out our table, made some guesses with the suggested group. Don't stress too much about the suggested group. Do not stress too much. Then from here, we kind of just started to match things up. We knew these two had to go together because we had, sorry, the top and then these two hydrogens here had to go together because this one has three hydrogens on the adjacent carbon atom. Hydrogens on the, let me start highlighting actually. Three hydrogens. So let's focus on each one. So looking at the three at the top, we do indeed to fulfill those two hydrogens on the adjacent, and it's also just an alkyl group. We don't have to worry about shift. Okay, this is better. Okay. Then for these two, this works out because we know we're going to have these two hydrogens connected to a carbon with three in the adjacent. That works perfectly. We do indeed have those three in the adjacent. And we also know that these two will be bonded to that oxygen. So we have hydrogen, hydrogen, carbon bonded to the oxygen. That fulfills or satisfies that. Perfect. So then moving on, we have this one hydrogen, which we knew was bonded to a carbon, then double bonded to an oxygen. Had to be here because we had that ester bond, okay? You didn't have to have the ester bond, I just chose to do it. As you saw in the answers, there were different ways you could do this. This is just the way that I did, and it happened to work. There are multiple answers for this specific question. Then with the CH3, we knew this would have to be at the end of the molecule because it only had one hydrogen adjacent and CH3 it has to be at the end, okay? So we satisfy these three hydrogens with one hydrogen on the adjacent carbon in four different colors. Yeah, just do each environment here. So, here we go. Okay, guys, this might be a better way to do it now. Okay, awesome. Three hydrogens, two in the adjacent. Guys, let me just give me thumbs up or like tell me move on if you want me to move on. Three hydrogens, two in the adjacent. Then we connected it to this bottom one here. Two hydrogens with three on the adjacent. We knew this had to be bonded to an oxygen as well, so we used both of these pieces of information to match these up and then form that oxygen. Then we kind of looked at the other side of the molecule. We still knew we needed that nitrile group, and we had to satisfy these two things. So we knew this was going to be at the end of the molecule, guys. Three hydrogens. So we can almost draw each three at one of the ends. You can almost leave the middle bit blank and then kind of mix it around there, because that CH3 had to be at the end. We could bond that to a carbon, which we know only needed one hydrogen. Only needed one hydrogen, guys. Okay? So these two we knew would have to match up. But then this carbon would have to be bonded to do the two different things. At this point, we have all of our hydrogens already used up. So bonding to two different things, we still need to satisfy that nitrile group. But then we also need to satisfy that carbon double bond to an oxygen. And that perfectly works for this shift of that single hydrogen. So we're just combining all the pieces of information that you know into one molecule. Thumbs up if you want to next question. Thumbs down. Well, we're gonna have to move on, but let me know, let me know. Just building the pieces, and whenever we see functional groups that can go at the ends of molecules, that definitely helps. Definitely experiment around with NMR, guys. Definitely experiment around. Highly recommend that. Okay, cool. Guys, let me know if the explanations are horrendous. I will try to go be more careful as I explain. But if they're okay, then let me know. Let me know. Thanks for the stuff, guys. Apologize already. On to the next question. Just try to be very careful. So as we go, I do have all of these questions on a document. I will share it after. This is what we just did, right? Yeah. So get rid of these and move on to the next question. Apologize. Just give me just a second, guys. That was our cyanide ion. Okay. Our next question. Let me zoom in. You guys can have a read. It's a pretty interesting question, guys. It's just a proton NMR. There is no mass spectrometry or infrared. We only have a proton NMR. It's going to be quite interesting. So yeah, yeah, can use different highlighters for colors for next. Okay, cool. Different highlighters for each. Yeah, perfect. Is it pretty much always an ester? It's not always an ester. I wouldn't say it's always. I wouldn't say it's always. Be careful with that. It's not always. NMR is one of those. Oh, sorry. Let me make sure. NMR is one of those things you just have to be very careful and definitely just draw out some molecules. If you have the molecular, you know the functional groups in it, and you have your proton NMR. Sometimes just drawing something out and seeing why something is wrong, and then fixing that problem, just doing it really quickly in the exam, could get you the marks you need. But yeah, guys, thumbs up or just say move on or thumbs up if you want me to start going through this. I'm going to have to. These take a while, so I'm just gonna have to keep them going. Okay, let's do it. A chemist isolates compound H from a mixture, sends it for analysis. Initial analysis shows the molecular formula, okay, is C10H12O. Amazing. They gave us the molecular. It's going to be quite helpful. C10H12O. Let me try and write this nicer. C10H12, and then we have the okay. Carbon 13 has 8 separate peaks. Okay, so we have 8 carbon environments. 8 carbon environments. I'm not going to write out the whole thing, I'm just going to write N. The carbon 13 NMR spectrum of compound H, we have that. The proton NMR is shown below. Let's fill it out, guys, and let's fill it out. Maybe start from the bottom, maybe start from the left or the right, sorry, either way works. So let's start from the right. We have a triplet with 3 hydrogens at 1 point, let's call it 1.3. So what was that? We have 3 hydrogens. We have the trip. Therefore, we're going to have 2 hydrogens on the adjacent. I'm seeing that 3 immediately, guys. I'm thinking that's going to be at the end of a molecule. Chemical shift. What did we say? Was it 1.3 or something like that? So what do we know it's going to be? So what do we know? It's going to be that H, H, H. Then moving on. We know there's going to be 2 to the adjacent carbon. And this carbon will be bonded on to something else. Okay? Not quite sure what, but that's going to be bonded to something else that's not a hydrogen. Then we have 2 hydrogens, quartet. Let's write that down quickly. 2 hydrogens, quartet. Just going to write out quart and then put 3 on the adjacent. Chemical shift, what we're thinking? We're thinking 2 point, oh my god, we're thinking 2.6. Doesn't particularly matter, we'll be able to find out. 2.6, what does that mean? What does that mean? Okay, there's a few things we could have here. A few things we could have. We know we have that single oxygen, so it could be involved here. But before we do that, I would recommend, guys, when we start thinking if there's an oxygen involved, let's check that higher shifts or further to the left shifts. Because that may tell us that the oxygen might not be involved here. And we can also see, oh, okay, we can also see the shift at 7. Let's leave that blank for now, and then it's going to give us some answers as we go. Doublet 2 at around, what is that, 3.7? Oh, okay, wait, let's read the full question, guys. Let's read the full question. The proton NMR spectrum contains a peak at 0 ppm resulting from a chemical added to the sample. State the chemical responsible for the peak, and state why it was added to the sample. Let me know, guys, as I go on to the next part. I'm going to read the next part, but write the answer to this question. I'll check it out. In the proton NMR, the peak at 3.7 would normally be expected at 1 ppm to the right. Okay, 2.7. So the thing that I was just about to write for 3.7 is going to be 2.7. We have to use the information in this question to determine the structure of compound H. TMS, perfect, TMS. TMS is exactly it. It's that reference that will be showing up at 0. Perfect, perfect, perfect. So we were about to write 3.7, it's going to be at 2.7, and this would be 2. So the fact that it shows up at 3.7 makes us a little bit suspicious that it might be next to other things that may be pulling it further to the left. Something just to keep in mind. Then we have that doublet. Just going to write dub. Therefore, one hydrogen on the adjacent. Let's leave that blank for now, guys. I think these later on peaks tend to answer the earlier on peaks questions. So then we have four. Then we have this. I believe that is a quartet, but it's kind of disgusting, which makes me think benzene. So let's check that shift. We have four. What was the shift? The shift was around 7, maybe 7.1. What does that mean? 7.1 shift. Hopefully, it'll answer our prayers. Yes, it is indeed benzene. Okay, so we have four on that benzene. What does that mean, guys? Similar to the question we had before. Because we have four on that benzene, we know that four, we don't know which four, we have to be careful with that. Four of these will be open. So we're going to have two bonds onto our benzene. It's good information. Great information. So we don't really have to worry about this. We can just call it a multiplet, or I guess it was a quartet, but doesn't particularly matter. I'm just going to put a dash there because we know it's benzene now. And then all the way at 9.8, I believe, that's a triplet with one hydrogen. Okay, let's fill it out. One hydrogen. We have the trip, so there's going to be two hydrogens on adjacent carbon atoms. Then all the way at 9.8, crazy. All the way at 9.8. What does that mean? What does that mean? Okay, 9.8. Awesome. Carbon double bonded to oxygen, and we have a hydrogen attached to it. So this is going to be the end of a molecule, which is another useful piece of information. We have that aldehyde. So we've quite a lot of useful information here, guys. 8 carbon environments. That might help us out. So let's go step by step, see what we can do. Maybe try and fill these two out. We have 2.7 and 2.6. We know there's going to have to be a single oxygen involved. Only one oxygen. And we know it's going to be on the aldehyde. So neither of these can be oxygens. So see, sometimes doing the later thing and then going back, we now know that the oxygen cannot be involved here. We don't have an N. So it's going to have to be those two which are bonded to our benzene. Why is there one at 2.7? Why is there one at 2.7? That's the benzene. And also it tells us in the question 3.7 is actually at 2.7. Probably because it's going to be next to other things that cause it to shift further left, but in terms of the actual functional group, it would normally be at 2.7. Little tricky thing in the question. Gotta be careful with this. But okay, so now we know that both of these will be bonded to a benzene. So we're going to have a carbon with two hydrogens. And the same thing here, we're going to have a carbon with two hydrogens. And then each of these will be bonded to our benzene ring. Great information because we knew that oxygen was going to be somewhere else. Bro, did you get these right when you first did them? I did, but I definitely didn't draw them out first time. I would draw it out. I think for this question, I drew two of the bonds in the wrong place, and then I was like, okay, this doesn't make sense. Go to the next. So now it is me doing it the first time. But when I first did them, I normally had to draw one thing out. I'm like, okay, that doesn't work. We go on to the next. So it's about quickly adapting and quickly realizing if everything worked out. And then we know this one's going to have 3 next to it. Okay, this is amazing. We've actually completely filled up one branch because we know these two hydrogens here will have 3 on the adjacent. So it has to be like this. So we can already draw this out. So let's draw out our benzene ring. We know there's going to be 2 things bonded to our benzene. Why? Because we had this 4 with the benzene. We needed 4 open carbons. We knew that we had 4 open carbons on our benzene. We also have the molecular. I'm going to write the molecular down here. What is it? C10H12O. We know we're going to have that aldehyde, which must be at the end of a molecule somewhere. We know that because of this shift, at 9.8. So let's just try to draw this out. We do also get given those 8 carbon environments. So we may have to change our answer if we have more or less than 8. But let's just go for it. So from here, guys, let's just put it here. Doesn't particularly matter. Let's give it a go. So we actually already know one of our 4 branches, which is great. We know we're going to have the CH2. So like you guys asked me to, I'm going to highlight. So we have these 2 hydrogens. We know we have the 2 hydrogens up here, bonded onto the carbon, which is bonded to the benzene. And then we know it's going to be connected to that CH3. And that CH3 is indeed all the way up here, which is fantastic. We can actually match these 2 up instantly. That is great. Really, really fortunate that they gave us that. Really, really lucky. Does the benzene not have hydrogens attached to it? It does, but we have that variable. It can either be a singlet or a multiplet. So we don't have to particularly worry about that. That's why in this case it will be, it says quartet here, and it will be a quartet overall, but I tend to leave the benzene splitting out of it because it can be very variable. And I think in exams they like to give it as a singlet sometimes, a multiplet, so it tends to be a bit iffy. My molecular is wrong. Oh, sorry, yeah, H12. Thank you for telling me. C10H12. Sorry about that. C10H12. Okay, so we have this already sorted. We also have, with the benzene, I'll do it in the green pen. We have those four open ones. So let's leave four open. Let's leave this one open, this one open, this one open, this one open. Because I'm purposely going to do it wrong. I know the answer. I'm going to purposely do it wrong so then we can analyze it from there. So let's just attach on. We know there's going to be something else bonded here. What do we know? We have these two hydrogens bonded to that benzene as well. Okay, so let's highlight that. We know these are also going to be bonded, so we have that carbon with two hydrogens, which have that benzene adjacent to it. This is good. How many carbons do we currently have? I like to check this from now and then. We have 6 in our benzene, 7, 8, 9. We only need one more carbon. So this has to be bonded to a carbon, of course. And then what do we have left? Finishing off the highlighting, guys. These two will be the blue. The benzene ones we're not going to highlight because as we already established what those are. And what do we have left? We have that aldehyde. So that's going to be double bonded to an oxygen and then double bonded to a hydrogen. Does this work? Now let's check, does this work? So focusing on this one hydrogen, we know we had two hydrogens on adjacent carbon atoms. This does indeed work. We can see with this hydrogen here, we have one, then we have two. Okay, that's not nice. We have one and then we have two. With these two, looking back up here, we have a doublet, so they only had one hydrogen on the adjacent carbon atoms. Okay, these all work and these are all sorted. We know our benzene, bing bong bing, has four open carbons because we established there are four hydrogens in that environment. Sorry, it has four open carbons because it has four hydrogens in that environment. And then we were able to match these two up because we can check the splitting patterns. This carbon was bonded to the benzene and it had three hydrogens on the adjacent. And then just simply matching it up, this one had three hydrogens and two on the adjacent. We knew this had to be an end of a molecule. We knew this had to be an end of a molecule. That's just about it. However, guys, we're not done yet. We're not done yet. Exactly. Ah, Oscar is on it. Oscar is absolutely on it. Let's count the number of carbon environments. So we have one, we have two, three, four, we have five, six, well, we could just count all the way around. 7, 8, 9, 10. So we have one, two, or two too many. So the only way, if we want to get rid of these number of carbon environments, the way we can do this is by symmetry. Because by symmetry, two carbons will then have the same environment. So let's redraw this out really quickly. We have our benzene ring. Oscar was on it there. Oscar's locked in. So if we draw them opposite to each other, just going to draw it out like this, guys, just to make things a little bit faster. CH2 and our CH3. Then we have our CH2 and our CHO. How many carbon environments do we have this time, guys? Let's count it. We got 1, 2, 3. These will both be the same. These will both be the same. 6, 7, 8. Exactly the number of carbon environments that they gave us in the question. So this will be the molecule that we need. Thumbs up if we are happy with that. Thumbs up if we are happy. Oscar is locked in. Oscar's getting that A star. He saw it very nicely, very quickly. Thumbs up, thumbs up, thumbs up. Got two more NMR questions. Are we happy with the explanations? Or should that be something I should be doing instead? Let me know, guys, let me know. I'm going to make sure the stream isn't lagging. It's my first year doing this, guys, so I apologize if the explanations are lacking. But I'm trying my best. I'm trying my best. I hope these examples are helpful. But remember, when we see that benzene, they may give us a singlet, a multiplet, or in this case, they gave us a quartet for some reason. Someone wrote Oscar deserves an Oscar, and the message was retracted. Sorry for calling you out. I think it was actually quite a funny wordplay, so don't worry. It's appreciated. It's good? It's a good explanation? I hope so. I'm trying my best. Let me turn that lamp on, it's getting a little bit dark. Alright guys, thumbs up if you want me to move on as well, thumbs up. Let's go to the mark scheme as well. Let's go to the mark scheme. See if I can find the correct mark scheme. I believe it's here. Okay, this is the mark scheme, guys. If you're curious about it's very blurry. If you're curious about what gets given marks, try zoom in if you can. But yeah, let me know. I'll leave the mark scheme up for just a minute. We're gonna start the next one in a minute's time. How do I know benzene has four open carbons? Because we had four hydrogens in that environment. They told us there were four hydrogens. Four hydrogens in the same environment meant because we knew it was on the benzene ring, because of the shift, there would be four. That's how we knew it's four. Okay? If it would be five, then there would only be one branch coming off our benzene ring. Three, then we'd have three branches, and so on. I hope that makes sense. So we knew it because there were four hydrogens in that environment on the NMR spectrum, on the proton NMR spectrum. I'm not going to read out your name, but I appreciate the nice comment. Guys, say move on if you want me to move on. Remember the chat is delayed, so I sit here for like 20 seconds before I see it. I do hope this is good. Two more questions. Um, Both of them only have the proton NMR because that's what we're focusing on. That's the hard bit. So yeah, I'm just waiting for any moves on or thumbs up. Okay, Raheem is happy to move on. Hey guys, I do hope this is helpful. I apologize if it's not helpful, but I'm sure most of you will be fine if you're getting this. Oscar's definitely going to be fine. He spotted that fast. I'm sure many of you spotted it. Just Oscar wasn't vocal. Now we'll see. I'm not going to take anything away from Oscar. So we have two more, I believe. Yep. Just deleting everything, guys. I apologize if it's ugly. Slowly shifting it across. Just give me a sec, guys. I hope it's all right. Okay, let's move on to the next question. I'm going to put it on the screen. Let you guys have a little read. I'll read it out as well. Oh, okay, Oscar. Okay, Oscar. Oh, I know. Yeah, yeah. Mr. Collar, the goat of chemistry. He explains it a lot better than me, I'll say that. Does this have Collar's approval? No. Oh, no, it does not have Collar's approval. I did not think Mr. Collar, I didn't think I was that recognized. Mr. Collar was a great teacher, really good teacher. The proton NMR spectrum of compound C10H12O2 is shown below. One of the signals has been enlarged to help its analysis. So we have this 1, 2, 3, 4, 5, 6, 7. We have a heptet, so six hydrogens on the adjacent carbon, which does make sense. Okay. A signal at 0 ppm results from TMS. TMS has been added to a sample of compound L before the NMR spectrum was run. Why was TMS added? Let me know, guys. Let me know why TMS was added. Oh, okay, okay. Mr. Collins is probably the chemistry teacher who got quite a few people in Oxbridge in my year. I'll say that. The proton NMR spectrum includes an integration trace. What information can be deduced about compound L from the integration trace? Sorry, this is not OCR, this specific question, guys, so I wouldn't worry too much. So using the information given in parts A, B, and C of this question, don't worry about that too much, just focus on the NMR spectrum. We have to determine the structure of compound L. So I'll leave it up for just a second, guys. Yeah, you can say it's a standard, you can say it's a reference. Reference and standard are both fine. You can say either one. Yeah, perfect. Zero shift, reference is zero, standard reference, all of that is perfect. That's all perfect. All gets you the mark. I do have the mark scheme afterwards, but just gonna go through the question first. Okay, let's go through this, guys. Gotta be getting through these questions. Alright. Start from the right. We can start either side, but let's go from the right. Six hydrogens, I believe that is a doublet. Apologize for the poor quality. So we have six hydrogens. Just gonna write dub. That means we're gonna have one hydrogen on the adjacent. Chemical shift, like 1.2. We have 1.2, suggested group. It's gonna be the alkyl group. Six hydrogens. I'm always, guys, when I see six hydrogens, the first thing I'm thinking, it could be something else. They don't have to necessarily be next to each other. But when I see those six hydrogens, I'm always thinking, we're gonna have a carbon like this. So there's gonna be two ends of the molecule. And we know there's gonna be one hydrogen bonded on the adjacent. So our relevant hydrogens, can already highlight this now. Let's do yellow. Oh wait, let's do yellow actually. So relevant will be these six here. Okay. So this is kind of all in the same environment with one hydrogen on the adjacent. I'm already thinking that when I see this kind of shift. I'm sure you guys have seen the one with 9 in past papers, where it was three CH3s coming off that carbon and the chain extended on. Okay, moving on. We have, oh, this is not a nice one to count. We have 1, 2, 3, 4, 5, I believe, maybe 6. Either way, this is a multiplet with one hydrogen. I believe this is a septet. 1, 2, 3, 4, 5, 6. Looks like a septet. This will be more clear in your exam, guys. I'm going to put multiplet slash septet. I'm going to see what happens. So I'm going to go multi. So there's one hydrogen slash set. So we can think this does make sense, guys, because we're going to have something for this single hydrogen here. So we can already match these up. So therefore, this one hydrogen, which we have over here, will have to match up with this hydrogen on the carbon over here. So this does make sense. You would think these would match up. Where's the shift? 2.6. Cool. So we have 2.6. What is 2.6? Going back down. Okay. Do they tell us anything about the molecular formula? Let's go back to the question. I believe they already told us. C10H12O2. Okay, so we have oxygens. C10H12. Oh my god. H12O2. Suggested group. So we know we're going to have oxygens. We're not going to have a nitrogen. And we're also not going to have a benzene, I believe. We could have a benzene, but looking at the rest of the proton NMR, this is going to be at 7.3. So this would tell us if we have that benzene ring or not. 7.3, we do have a benzene ring, so that is something that we have to consider. So let's just move on now before we suggest any groups. I'd always recommend, if you're a bit confused, just move on to the next one. Let's suggest some groups. I'm working through these questions with you guys, so let's just see what we can do here. It did give us the zoom in, so we are going to have to use this. 1, 2, 3, 4, 5, 6, 7. But it's a benzene ring, so it makes you think it's going to be a multiplet. Oh, sorry, this was the expansion. Yeah, I didn't read the question, guys. Be careful with the question. This was the expansion at 2.7. The reason they give you the expansion is so we can use this information. So because we can count 7 here, that's how we know it's going to be septet. Therefore, we do have to take into account those 6 hydrogens on the adjacent carbons. And then this one here, this is just a disgusting multiplet, or it could be a singlet in your exam. That's going to be the benzene ring. And we have 5, so drawing out that benzene ring. So this one we don't have to worry about at all. It's going to be multi. It's around, what is this, 7 point, doesn't particularly matter, 7.3. 7.3, and we know there's going to be 5 in that environment. So what do we know? 5 of these carbons will be open on our benzene ring. Let me just draw out that ring. Okay. So we know 5 will be open. This is actually quite useful information. So already before we even start, I can draw a benzene ring, and we know there's going to be only 1 which has something bonded to it. So this is already useful information. Esters, looks like people are happy with Ester. Beautiful Ester NMR incoming. Looks like it might have to be because we have 2 oxygens. I'm not sure where else we can use these things. So we're gonna have to have an ester. Now looking here, we have to have something with an oxygen involved. This was at 2.6. Looking at 2.6, it's not going to be that single bond to the oxygen. It's going to be that double bond to the oxygen. So carbon double bond to the oxygen, not the carbon single bond at 2.7. So essentially, matching these up, we know this carbon will then be bonded to an oxygen with 1 hydrogen onto it. And then because it has 6 on the adjacent, this carbon will indeed be that carbon that we have just above. So we've actually been able to match it up. Nothing scary here, guys. Nothing scary here. So because we know there's nothing, or sorry, we don't have a carbon with hydrogens attached directly to that single bond oxygen, the only explanation for this can be attached to the benzene. So from here, we are going to have to be attached to a carbon, which is then double bonded. We have that ester, because we know we have those 2 oxygens, so these will have to match up. We still don't have any hydrogens here. We do have those benzene hydrogens, once again. These are going to be the 5 open ones, because we have 5 on that multiplet where benzene normally is. Then from here, how many carbons do we have? We have 10 carbons. So how many do we have currently? We already have 7 carbons. So we can only have 3 more. And looking up, we know these 2 are going to have to match. Sorry guys, that should be a double bond. We know these are going to have to match. Is everyone happy? I'm using Dr. Harris's advice. Dr. Harris was also quite good. Or she was good for my class, that's for sure. Great to see some Marlingtonians in the chat. Oh, Jesus. Okay. So where were we, guys? Got a bit distracted there. Okay. So then we had that one hydrogen, which was bonded to that hydrogen on the carbon, which is double bonded to the oxygen. And we also knew we are going to have those six hydrogens on the adjacent carbons. I'm not going to draw it all out, it'll just be that CH3. That is horrendous. CH3, okay? So we already know this. So then I'll draw it out. So we know we have the ester bond for those two oxygens. We know we don't have any hydrogens which fulfill being attached to a carbon and then single bonded to an oxygen. So we can't have that. And then we knew from the start that these two would match. So just highlighting everything out. So yeah, I actually need to be drawing a bit more careful here. 5 bonds. Yeah, sorry guys, sorry. Just being careful here. Alright, so there we have it. Our C10H12O2, two oxygens, 6 carbons, 7, 8, 9, 10 carbons, 1, 2, 3, 1, 2, 3, plus 5. Sorry, 1, 2, 3, 4, 1, 2, 3. There's a 7 plus the 5 gives you 12. It's hard to be speaking and drawing and doing it all at the same time. I do apologize. Now, single hydrogen, which has a 6 on the adjacent, would indeed be here. That'll be your final molecule, guys. Does that all make sense? Can't go on like this, can it? It can. We got one more, boys. We got one more. Thumbs up if you want me to move on. Thumbs up if you want me to move on. This is what we had, guys. Nothing crazy. How do we know the oxygen is directly in the benzene ring? Because none of our other environments that we had were single bonded to an oxygen. This one at 2.6 had that hydrogen onto the carbon, which was then bonded to a carbon, but double bonded to an oxygen. Okay? So we couldn't have a carbon which had a hydrogen onto it, which was then single bonded to an oxygen. You could have tried it out the other way potentially. I'm seeing some thumbs up. So that's how we knew. Move on. Okay, move on. Last question, last NMR question, guys. Then I got some unseen mechanisms. I do hope this is helpful. I do hope this is helpful. I'll show the marking for this question quickly, if you're curious. I can find it. There we go. So a few different things you guys can have. Oh, sorry, no. This one where you had the oxygen and double bonded to the oxygen, sorry, which we knew our hydrogen is bonded to a carbon, which then bonded to a carbon, double bonded to an oxygen. So you couldn't have it this way round. You'd only receive 1 mark. But if you have it the correct way round, because we had the shift with a hydrogen bonded to a carbon, bonded to another carbon, double bonded to an oxygen, was the correct way. Carbon, carbon NMR is good. All right, cool. All right, let's move on. Last NMR question, guys. Last NMR question. Give me a sec just to delete this up. Oh, I don't think Mr. Connor would be too proud of me, to be honest. All right, guys. Here's the next question. Once again, it's just an NMR spectrum. Nothing crazy. Now, the key thing here, I think in a previous part of the question, guys, it said there were no nitrogens. It was just made up of carbons and hydrogens on our ester. So saying that the functional group was the ester, it tells us the chemist obtains a mass spectrum and a proton NMR spectrum of one of the esters separated by gas chromatography. In this question, it told you there were no nitrogens, okay? The mass spectrum has a molecular ion peak at 164. We're going to have an MR at 164. Here's a proton NMR. We have to analyze this to identify the ester. So they already tell us it's an ester. So what we have to do is use the information given and see what we can do with the information. Okay, I'm going to start going through this now, guys. So what we can do is, because we know there's only oxygens, hydrogens, and carbons, we have 164. Of course, we know the ester bond is that C double bonded to an O, then single bonded to an O. Okay, so we have two oxygens. So what we can do with that 164 is we can actually take away 16 times 2, take away 32, but we have those two oxygens. And then we kind of use this to find the reasonable number of carbons and hydrogens. So pulling out the calculator, 164 minus 32, and then we're going to divide it by 12. So we have 132 divided by 12. If we divide 132 divided by 12, we get exactly 11. But that would leave us with no hydrogens. So it makes sense to have C10, H12O2 as our molecular formula. So we use the NMR, we use the fact they told us it was an ester, and we just see a reasonable number of carbons and hydrogens. If you had 9, you'd have way too many hydrogens, it wouldn't make sense, and so on. They don't always put NMR at the end. They can put it in the middle of the exam. There was one where they asked you to find two structures. I think they were structural isomers. One was cyclic, one was an alkene, and you had to use that in the middle of the exam. So it's not always the end. So we have a molecular formula. Let's do the proton NMR. Guys, I will say when you see this shift at 7 point something, I recommend just drawing that benzene ring on straight away. But if not, then it doesn't particularly matter. It just helps to understand we're going to have that benzene. So 3 hydrogens. Here we have a singlet. Therefore, we're going to have no adjacent hydrogens on carbon atoms. Chemical shift at 2.1, 2.2. So what do we know about 2.2? There's a few things we could have. This is why we're going to move on. Sometimes it's good to leave these things blank until later on. There's quite a few things we could have. It could be a hydrogen on the carbon bonded to the carbon, essentially part of that OH part of an ester bond, or it could be the one directly bonded to the benzene. But let's just move on and go back to it, because sometimes it helps just to carry on a bit. Then we have 2, that is a triplet. 2, trip. That's going to be 2 on the adjacent. Chemical shift, what, like 2.8, 2.9? Let's go 2.9. So what do we know about this one? It's going to be the same problem as before. Same problem as before. It could be either one of these, so we're going to see what works. Let's move on then. Then we have 2 hydrogens, and it looks like a triplet. I do believe it's a triplet. So same thing, it's going to be that 2. What is the shift? The shift is 4.4. Seems appropriate. So at 4.4, we know we don't have an alkene, we have the ester. Okay, so here we have the hydrogen on the carbon, which is then bonded to the oxygen. So we're going to have 2 of those. So we know we're going to have this, guys. We're going to have 2 hydrogens on the oxygen, and then we have a triplet, therefore there's going to be 2 on the adjacent. So we know we have this, and we also know we're going to be bonded to a carbon, because there's only one bond left, which has 2 hydrogens onto it. Good information. This will keep on extending, but it's already quite useful stuff. Then we have this multiplet, a disgusting one, at around 7, we know it's going to be benzene. So how many do we have? 5. Therefore, there's going to be 5 open carbons on our benzene. So we're only going to have a branch or a bond on one. Can't see the thing? What do you need to see, guys? What do you need to see? Let me know. I'll leave this up for a second if you want. Okay. So this was a multiplet. This is a multiplet. We don't particularly worry about this because the shift is going to be at 7.3, let's just call it. It doesn't matter. And that is indeed our benzene. When we see that shift at around 7, we're immediately thinking benzene. So we have that benzene. And because it has that 5 in that environment, we're going to have 5 open carbons. Okay, so we can immediately draw that on when trying to think about a molecule. I always like to draw that benzene on first. We don't know how it's going to be involved. We know it's going to be bonded only on one carbon. Now we kind of have to work through. So we know we're going to have a hydrogen onto a carbon, which is then bonded to a benzene. Now, because these shifts, well, we know it's not going to be the CH3 one, because as we established, guys, this has 3 hydrogens onto it. So we're going to have a carbon, which is then bonded to 3 hydrogens, and it's bonded to a carbon which has no hydrogens onto it. We don't have to worry, because this would have to be the end of the molecule. So we know, because this has to be the end of the molecule, it's going to have to be involved in this double bond O, because we have that ester, so it's going to have to be involved in the double bond O here. So we bonded to a carbon, which is then double bonded to an oxygen. We know that because if it was just the CH3 and we put this on our benzene, it'd be the end. And then we'd be stuck and we wouldn't have the rest. So then from here, we know this is going to have to be this shift here. So there's going to be these two hydrogens. So we can already highlight these on. It's going to be these two hydrogens here, shift 2.9 because we're attached to that benzene, and we're able to establish that. I'll draw it onto here now. Just a rough drawing, guys, to get the idea. Okay, so we already know this. This is good. This will then be bonded, sorry. We're going to have two hydrogens on the adjacent carbon. So there's only one more bond left, so this has to be bonded to a carbon. We're going to have to keep on going the chain. And we know we're going to have two hydrogens on the adjacent. So this has to be the case. Now let's look at where else we have two hydrogens in the same environment. That'll be focusing on down here. Focusing on down here, we know we're currently at this row essentially. And then from here, what do we know? Well, we know these two hydrogens will be bonded to an oxygen. And we also know we're going to have two carbons on the adjacent. So do we already fulfill that? Let's check that out. We do indeed have two carbons already on the adjacent. So looking at this one, we do fulfill that triplet for each of these. This one is bonded to a benzene. So last step, we just have to bond this to the oxygen because we know from the shift it's going to be bonded to the oxygen. Useful stuff here. And we know it's an ester. So we can just fill in our ester functional group. Nothing scary. But yeah, we have also sorted out that benzene already, guys. We have already sorted out that benzene because we know we had those 5 hydrogens in the same environment on that benzene ring. So last one, let's compare our molecular. I like to just from time to time compare our molecular to what we currently have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 carbons, only one more carbon. There's only one more thing it can be. We have both of our oxygens used. And we also know it's going to be this blue one at the top. That's CH3. We knew it's going to be at the end of the molecule. And we know they have the shift of 2.2, which makes sense because we're bonded to that carbon, double bonded to the oxygen. So from here, this appears that everything kind of makes sense and falls into place. Let me know if that makes sense, guys. Let me know if that makes sense. What degree am I doing? I'm doing maths and econ, but first year was just maths. Second year, it's like 50-50. And third year is just maths as well. So it's basically maths. Let me know if that all makes sense, guys. Let me know if that all makes sense. That's the last proton NMR question that I have. I have 4 unseen mechanisms. These are a lot faster. These are a lot faster. You got one? Good to hear. Happy to hear you got one. They normally do put the 6 marker at the end for the NMR. They do like to do that. Sometimes they're friendlier, sometimes they're not. If you see that benzene ring like we did today with a lot of these shifts, it does tend to help you out. But yeah. I got 3 A stars on my A levels, guys, so I'm not. How did I do? I did get through 3 A stars. So it's fine. Still got rejected from a lot of universities, but I did get the 3 A stars. So I can I have the credentials to do tutor, more or less. So I hope that makes sense. Thumbs up if you want me to move on. Thumbs up if you want me to move on. I'm gonna quickly check the stream's not dying. Looks like we're all good. I have 4 unseen mechanism questions. They are not too hard, I will say that. Not too hard. I'm gonna put the mark scheme up for this question in case you guys want it. There's the mark scheme. Harris and Collar, guys. Harris and Collar. Guys, focus on chemistry. Don't be asking me questions. Lock in, yeah? I'm not answering all these questions, guys. Come on. Lock in with the chemistry. Just waiting for those thumbs up to know whether to move on to the unseen mechanisms. There's the mark scheme if you guys want it. That was all the NMR. I hope it was helpful. Let me know if it wasn't helpful, but smash subscribe if it was. But yeah. Okay, cool. I see thumbs up. Let's move on. Thumbs. Okay, awesome. Unseen mechanism, guys. These are not too bad in general. Okay, these are not too bad in general. Just a key few facts here that are useful. Guys, you got it's my favorite show. Okay, let's carry on. So we're told that one method for the formation of ethyl ethanoate, remember that alkyl group is the one bonded to the single oxygen, and then that O8 group is the one bonded to the carbon double bond to the oxygen, longest chains. In this case, it's two and two. They can mix it up. Moving on, one method for the formation of ethyl ethanoate is a reaction between ethanol and ethanoic acid, which is catalyzed by hydrogen ions. Fine, we know this. An incomplete simplified mechanism for this reaction is shown. We have to add curly arrows and relevant lone pairs, so no dipoles needed here. Add curly arrows and relevant lone pairs of electrons to complete the mechanism. Okay? So this is just a game of spot the difference. No dipoles, all we need are lone pairs and curly arrows. So spot the difference, looking left and right, what changes? This oxygen gains a proton and a positive charge. So what has to happen? We know we have a lone pair of electrons on our oxygen. It must attack that positive proton. So from here, that's absolutely fine. What happens here? What spot the difference once again? We form a H2O, and then we also form this positively charged oxygen because it has one too many bonds. It normally has two bonds, in this case it has three bonds. So all we have to do to get that water, we're gonna have heterolytic fission with both of those electrons in the shared pair. So we break the covalent bond, both electrons in the shared pair go to that oxygen because we're forming water. Then we know we're gonna have a lone pair of electrons on this oxygen, and it would now attack. We don't need dipoles, so we don't have to worry about that. It would now attack the carbon. That's all it is, because we can see we form water, has no positive charge, so it has to be heterolytic fission to remove that positive charge to just get a water molecule. And we completely bond all this H and C2H5. Nothing scary here. This is just what happens. Spot the difference in these, okay? Then moving on, spot the difference once again. Oh, we've done this, sorry. So spot the difference once again. What's happening here? What's the change? Carbon double bond to oxygen. We again get a H plus. It's a H plus, and we lose that positive charge on the oxygen. It's going to be heterolytic fission, breaking the covalent bond, both electrons in the shared pair going to that one bonded atom, in this case the oxygen, to lose that positive charge, and then we get our proton left because it didn't gain any of those shared pairs of electrons. Hope that makes sense. Hope that makes sense. Just curly arrows, so it's nothing too bad here. I didn't do A level econ. I don't know the A level something, and I've barely done econ. Most of I've like weighted my degree towards maths. So it's basically just maths to be honest. Okay. In an experiment, the oxygen atom in ethanol is replaced by oxygen 18 isotope O18. The products of esterification are we have the ester and we have water. Label the O18, oxygen 18, in one of the products. Justify our answer. Okay, guys, let me know. Let me know what you think. Let me know which oxygen is going to be. So the key thing here is we had ethanol. We're told that this O was replaced by the 18. Okay? So let me know, let me know. Oh, Jesus Christ. Boys, lock in with chemistry, yeah? Paper 2, sorry, is tomorrow. And we also had ethanoic acid. So what do we know about esterification? What do we know about esterification? We know for esterification we lose that OH from the carboxylic acid and we lose that single hydrogen from the alcohol. Okay? So therefore, if the oxygen 18, was put on our ethanol, it will be the oxygen not formed in the water. Exactly, on the X, yeah, perfect. So this would be our O18. And that's it. That's the first unseen mechanism. Let's move on to the next. Hope everyone's fine with that. Hope everyone's happy with that. So we're told that vitamin C, C6H8O6, is a weak acid. They give us the Ka value. We don't particularly care about the Ka value. It's often referred to as ascorbic acid. Don't worry about that. In aqueous solution, vitamin C donates a proton to water. So they give us this equilibrium here. Add curly arrows to the diagram and suggest the mechanism for this process. Once again, guys, it is a game of spot the difference. It's a game of spot the difference. So we see we get a H3O plus. Okay? So what do we have to do? So let's just keep spotting the difference, guys. We see we form a double bond between the oxygen and the carbon. We also see our oxygen becomes negative down here, and this double bond shifts along one. So we can almost just, we don't have to properly understand this, guys. You can almost just kind of see the difference and just realize what has to happen. Because we see we form a double bond between the oxygen and this carbon on this like cyclic structure, right? So this is going to happen. We're going to have to form a double bond. We're going to have this heterolytic fission and this lone pair because we get a H3O plus. So this will have to attack. Just curly arrows, guys. We don't need any dipoles. So this will have to pick up this proton. The lone pair, remember, curly arrows from a high electron density to low electron density, showing the movement of a lone pair of electrons. We'll have to go from the lone pair to the hydrogen. We're going to have to break this double bond. If we currently have this oxygen double bond, this carbon would now have 5 bonds. This can't be the case. But we do see that this double bond actually moves over. So that double bond will have to move over to here. And once again, this carbon now, looking over here, guys, would now have one too many bonds. So we have to break this double bond heterolytically once again, so our oxygen gets that negative charge, accepting that lone pair of electrons that we break from the pi bond. Hope that makes sense. Hope that makes sense. This is, you can almost just compare, like the only way you can do this and then kind of work from there. Okay, let's keep on going. Guys, let me know if I'm too fast or too slow or just anything like that. I'm seeing a lot of people just chat. This is unseen mechanisms. They will give you an unseen mechanism in your exam, and this is just a bit of practice. I mean, this is kind of using the idea of that nucleophilic addition as well. Same kind of idea, I guess, with this oxygen, right? Yeah, this is a ridiculous like mechanism. It's stupid, but it's just spot the difference. Just see what happens. This is actually how the 2, 4, 6 electron donating groups work, increasing the density at carbons 2, 4, and 6 to make them more susceptible to electrophilic attack. Can you do the ones where they don't give you a diagram to spot the difference on? I'll only have these questions prepared. I'm sorry. I've only got these 4 prepared. This mechanism, Jesus, it's a good question to be fair. It's a great question. This isn't one we need to know, guys. It's unseen, so it's just a game of spot the difference. With chemistry, they like to give these questions. It's meant to just be like a thinking task, just your ability to see what to do. Thank you, Dylan, for defending me. I appreciate that. Okay, so we have the aldehyde group takes part in condensation reactions with many compounds containing an amine group or a methyl group adjacent to a carbon double bonded to an oxygen. In these reactions, water is formed as a product, as we see here, and 2 examples are shown below. Okay, nothing scary. Predict the organic products formed in the following condensation reaction of benzaldehyde. In each reaction, an excess, okay, it's always important. There's a reason they're telling us excess. I'm going to underline it. An excess of benzaldehyde is used. Draw the structure of each organic product in the boxes. Yeah, it's just applying that knowledge. Just applying that knowledge. Okay, guys, so what do we know? Let's look at what they tell us. So simply looking at what they tell us, we have it reacting with NH2OH. So we have this benzaldehyde. It probably would help just to draw it out. Let's just draw out so they want the organic product. Yeah, let's draw it out. So we have our benzaldehyde. Nothing bad there. We know we're going to add that N2OH. And what do we know? It doesn't react with the OH. It doesn't tell us anything about the OH. This is literally them giving us information and then having to use it. Okay, it doesn't tell us anything about OH, but we do know with that nitrogen, we form that C, double bond to an N, and H2O. So from here, comparing to our benzaldehyde, what reacts? We get rid of this oxygen, and we get rid of these 2 hydrogens. So we literally just draw out using the information they give us, and then spotting the difference essentially. So we have that carbon, we lose that double bond to the oxygen. We then have a hydrogen just going up here. It's not completely in the box. Then we're going to be double bonded, just using the information they give us, double bonded to that nitrogen. And we're still going to have that OH bonded to the nitrogen. But we're going to lose both of the protons, as we saw on our, in this case, NH2OH. And we're going to form this product. Okay, moving on to the next. Here we have CH3COH, so here's our benzaldehyde. It might help just to draw it out sometimes, guys. No one really appreciates them just given the structural. It's not ideal. This isn't even structural, this is more just bit of a mixture, isn't it? I guess they just draw the benzene as C6H5. Okay, so what do we have here that we know reacts? So we have ethanoic acid. Well, we know we're going to have that CCH3. Okay, okay. So it's always good just to draw out what we currently are reacting with. So we have that ethanoic acid, and we have that CH3. We know when we have that carbon bonded to a carbon, double bonded to an oxygen, that bond will indeed break. And then this carbon will then be. So what do we lose there? So what do we lose? We lose this oxygen here. That double bond will be formed with this carbon, and we lose two of these hydrogens. It's just about spotting the difference. Just about, yeah, it's not bad, guys. Just use the information they give you, kind of just match up what you have, and it's always key to kind of draw things out. Always helps in the exam to draw things out. This is the kind of thing that would trip certain people up to stop people from getting those like 95s or 100s. So we can just draw out our product. We have our benzene ring. Then what do we have? We have a carbon. So with the benzaldehyde, we did have it bonded to a single hydrogen. We lose that double bond to the oxygen. We now double bonded to a carbon. Which carbon precisely? It'll be this one here. That one loses two hydrogens, so it only has one hydrogen bonded to it now. Then once again, same idea, still double bonded. Oh wait, not there, sorry. One more carbon, there we go. So this one gets a double bond to this carbon, just using the information they give us, guys. Just using the information. And then from here we can have the same carboxylic acid, because we know it will react. That should not be double bonded. Same carboxylic acid. Nothing particularly different there. We're just using the information that they tell us. Okay, this last part is definitely the hardest part. They tell us it is in excess. They tell us in excess. Why do they tell us this? Well, let's draw out what we have reacting. Okay, we've got a ketone, guys. We've got a ketone. So let's draw it out. We have the CH3, then bonded to a carbon, then bonded to an oxygen, then bonded to another CH3. Now we know that this CH3 bonded to a carbon, which is then double bonded to an oxygen. These are, by the way, these are OCR questions, guys. Like they may not be in past papers, but they are OCR questions. Okay, so what do we know? We know that these carbons form double bonds with what we had on our benzaldehyde. But what do we know, guys? What do we know? Excess. We're in excess. So there could be more than one benzaldehyde involved. How do we know which groups react with which elements? It gives you the information. It will just give you the information. It's an unseen mechanism, or in this case, it's not even a mechanism. It's an unseen reaction. You just have to use the information. Yeah, ketone with benzaldehyde is a bit surprising. But because we have two of these groups that we're told will react, and we're also told it's in excess, they're telling us this information for a reason. These will be the harder questions on the exam. We know we're actually going to have two benzaldehyde molecules. So what do we have? We have that C, still bonded to the H. So same idea as here, guys, then double bonded to the carbon, this CH3, the carbon on this CH3. Still have one H, then we bond to the carbon. We still have that double bond to the oxygen. Gonna need to make some space here. But then from here, we're gonna have the same thing on the other side because it's symmetrical. And we know that when we have the CH3 to carbon to double bond oxygen with what we had on our benzaldehyde, same idea. This carbon will then be bonded. I believe this is correct. Yep. Only a single bond there, sorry guys. Then we double bonded to that carbon, still have that hydrogen on, then we have that benzaldehyde from before. So the key thing was they told us that was an excess of benzaldehyde. And we get left with this. Yeah, I mean, hoping I see OCR. Yeah, it's definitely a tough third mark, but it's when they say excess, you know something's going on. You know something's going on. All right, last unseen mechanism question, guys, and then I'm gonna ask if you guys want me to go through as many mechanisms as I can possible, but if not, then I'll just move on. So butane 1O, I really want to draw it out to be honest. But butane 1O reacts with sodium bromide and sulfuric acid to form one bromobutane by nucleophilic substitution. Okay, we know this, but there's going to be a twist. It's unseen. Step 1, the oxygen atom from the alcohol group accepts a proton to form a positively charged intermediate. Bromide ions react with the intermediate from step 1 by nucleophilic substitution to form one bromobutane. Okay, So let's do it out. So we have butane 1O. I'm going to try skeletal here. I'm going to see if it works, but it might not. So 1, 2, 3, 4, butane 1O, okay. Reacts with sodium bromide and sulfuric acid to form. Okay, let's just go with step one. Form one bromobutane by nucleophilic sub. So the oxygen atom from the alcohol group accepts a proton to form a positively charged intermediate. Okay. So probably would have been better to do it displayed. Displayed, guys, as we should with mechanisms. So this might just take a second. I apologize already. Carbon, carbon, carbon. Not all of these are relevant, so I can just draw these out quite quickly. And then this is bonded to the OH. Okay, there's your butane 1O. Very, very neat. Six accepts a proton from a positively charged intermediate. Okay? So what's going to happen, guys? What's going to happen? How do you know the nitrogen is with OH? What nitrogen? None of these, there's no nitrogen here, guys. So, guys, what's going to happen here? We're going to form that positive intermediate. We know oxygen has that lone pair of electrons. We have that lone pair of electrons. Curly arrow shows the movement of a lone pair of electrons. We're going to attack that positive proton. So now we have that positively charged intermediate. Why is it positively charged? I'm really not going to draw this all out. So what's this? 1, 2, 3, 4, 5, 6, 7, 3 plus 4. Okay, I'm just going to do CH7 to speed things up a little bit. Then this will be bonded to that carbon with two hydrogens. And this will have the oxygen, which has one too many bonds now, so it's going to be positively charged. Okay, this is good. Bromide ions react with the intermediate from step one to form one bromobutane. Okay, this is actually just completely fine. So bromide ions, negatively charged, lone pair of electrons, one bromobutane. We have to break this bond heterolytically. And these lone pair of electrons attack our carbon here. Then we form your one bromobutane. That's literally it, guys. There's nothing crazy about this. Yeah, exactly that. Exactly that. So what we left with, we have our one bromo. Okay, this time I'm drawing a skeletal. We have our 2, 3, 4, and we have our H2O. And that's it. So do you guys want me to go through some of the mechanisms, like the nucleophilic ones with sodium borohydride, or ketone aldehyde to hydroxynitrile, maybe some nucleophilic substitution, electrophilic substitution? Is there any mechanism you guys want me to go through really quickly, like before the exam? Let me know, let me know. Just gonna put my phone charging. If not, then I will be finishing soon. But if so, let me know. Yeah, it is indeed. Just gonna make sure the stream hasn't crashed. My laptop is getting very hot. Looks like we're all good. Motivational speech. We've established this, guys. Like, you guys don't need motivational speech. You have the determination already. No, you're not getting a motivational speech. I know there's some Marlingtonians here. I don't want that to be, it's gonna be clipped. Don't want that. Why is the arrow from the O to the H instead of the other way around? Because we have that lone pair of electrons on our oxygen. Curly arrows show the movement of a lone pair of electrons. Boys, you don't need it's paper two, guys. Like, it's not a speech. You guys probably have like 4 exams this week. No chromatography has been touched, no MCQs have been touched, and mine's gonna Fred, you'll be fine. You'll be fine, Fred. This mechanism, you don't need to remember this mechanism, it's an unseen one, so you just follow the steps they give you. It's almost like baking a cake, like I'm not even joking. You just have to take the ingredients and spit them out. So I think that's all good, guys. Are we confident for paper two? Are we confident for paper two? I feel like you'll be fine. You'll be fine. Maybe there'll be a speech before stats and mechanics. Chem is clear. Chem is clear. Guys, no, you gotta be motivated, guys. Like, come on, you gotta be motivated. Okay. I mean, chemistry paper one is done. You got one more paper. of organic. Then you mix the two combined. I'm sure you'll be fine. You guys have been watching the videos. I'm sure you've done every past paper. You know your all your reaction pathways. I mean, there's nothing that can really trip you up, guys. Like you're gonna be fine. I'm not gonna give you an Econ Plus down mango speech, but I'm gonna tell you you'll be fine. You know those mechanisms. You know those reaction pathways. You know the proton NMR. I mean, I'm sure you guys are only gonna drop 1 or 2 marks. You don't have to worry. All right, so I think we're gonna end it there, guys. I wish all of you the best of luck tomorrow. Um, guys, please say hi to Mr. Collar or Dr. Harris for me. That would be great actually. But yeah, they were both quite helpful. I'm gonna go through one paper then sleep. Appreciate everything. Guys, I hope these have been helpful. I really do hope these have been helpful. I make these videos for my CV to be honest, to make it look a little bit nicer, but that's about it. I do hope the Marling people do especially well. Sorry about everyone else. I want the Marling people to do the best. You got Harris and Colin, make them proud. Imagine them teaching you for 2 years and you don't get the grades you need. Yeah, no pressure, guys.